Hey everyone, and welcome back to the Foundry by Forge College. I am absolutely thrilled to have you here today. In this explainer, we're going to jump right into the ultimate blueprint for assembling a high-performance smart contract engine block on Solana. Now, as you know, we're currently working our way through the Advanced Anchor Concepts and Capstone module, which is a crucial part of Anchor Framework Essentials, sitting right inside the broader Solana Development Tools track. If you've been following along, especially after our previous lesson on security best practices, you know we've covered some serious ground. We've gone from optimizing code to structuring complex data to locking it all down securely. Well, today is the day we take all of that theory and forge it into concrete, deployable code. Because let's be honest, nobody wants their smart contract to look like a tangled ball of Christmas lights, right? So this is your mini project. Let's get into it. Okay, here's the master schematic for today's explainer. We'll start with the assembly blueprint, then move on to pattern to performance. After that, we'll cover the measure first refactor, followed by security as contract, and we'll wrap it all up with the final inspection. All right, stepping right into section 1, the assembly blueprint, gathering your raw materials. So let's dive into the setup phase. Over our previous modules, you've really put in the hard work collecting some vital artifacts. You've built actual tools and gathered critical data. But what exactly are we building today? Well, we're pulling all of those materials onto the workbench to construct a self-contained anchor module. This is your mini project. I want you to think of it as a tightly scoped, fully functional piece of your final capstone project. Maybe it's an on-chain indexer or, a slice of an order book. The whole goal here is to integrate your optimization techniques, complex data layouts, and security checks into one single testable run. It's really about proving that the pieces actually fit together perfectly, rather than waiting for the final capstone just to find out your code spontaneously combusts. To make this happen, we're combining 3 very specific ingredients today. First, we have our profiling artifacts from Lesson 1. Those are your benchmarking harnesses that measure compute units. Next, we have our modular state models from Lesson 2, which are your packed struct layouts for nested collections. And finally, our outputs from Lesson 3, the security checklist and threat modeling. These aren't just isolated homework assignments, guys. They are literally the gears, pistons, and casing of the engine block you're assembling today. Moving right along to Section 2, Pattern to Performance, the architecture phase. Welcome to the architecture phase. This is the moment where we take a step back and realize that how we logically organize our data directly dictates how it physically sits on the blockchain. I absolutely love this quote. The pattern is not decorative, it dictates your performance. It's so incredibly easy to look at software design patterns as just a stylistic choice, right? Kind of like picking the paint color of a car. But in Web3, and specifically on Solana, your pattern is your engine's plumbing. Whether you choose an accessor-delegate pattern for permissioned operations or an append-only log for your data, that choice entirely rolls your compute budget. It dictates exactly which accounts you read frequently and where your serialization costs are going to bottleneck. Okay, so how do we actually physically assemble this? Here is your high-level sequence. Step 1, sketch the API and write a short design note. You got to know what you're building before you start coding. Step 2, create your anchor program and state structs, specifically leaning on packed structs to avoid dynamic overhead. Step 3, instrument your code with those security guards we developed previously. And finally, Step 4, run your profiler harness. This exact sequence ensures you're building deliberately and not just throwing code at the wall to see what compiles. Which brings us to Section 3, Measure First Refactor, Tuning the Engine. Now that we have the physical assembly mapped out, it is time for the tuning phase. And listen up, because this is where we separate the amateurs from the professionals by demanding hard data over speculation. I really want to emphasize this. Stop vibe coding. What is vibe coding, you ask? Well, it's when you stare at your monitor, change a complex data structure to a simpler array, and just feel like the code is running faster. You kind of nod your head and say, yeah, the vibes are definitely more performant now. No, absolutely not. You need to consult your local profiler. Speculative micro-optimizations done without hard data will waste your time, needlessly drive up your gas fees, and often make your code worse. Measure first, always. Let's look at the reality of what tuning actually looks like. Your core performance criteria for this mini project is super simple. Identify a baseline metric and then reduce it. In our example here, we went from a baseline of 12,000 compute units down to a refactored 9,800 compute units. Now that is a tangible, measurable improvement. We are looking for at least a 15% drop in your compute units or a 10% drop in transaction size. Seeing that drop, that is exactly what success looks like. It's not a feeling, it's a visible, documented decrease in the resources your smart contract consumes. You must capture these exact before and after numbers using your local test harness, and you have to document them right in your module's README. If you don't have the data to prove it, the optimization literally didn't happen. Let's move on to Section 4, Security as Contract. Forging the armor. An engine without a safety housing is honestly just a very fast explosion waiting to happen. The absolute crucial point here is implementing these non-negotiable guards. These form the indestructible casing around your anchor module. Every single public instruction must have explicit authority assertions, basically asking, are they actually allowed to do this? Next is safety serialization. You must reject malformed bytes before they break your logic, or even worse, break mainnet. And finally, negative auth testing. You actually have to write unit tests that purposefully try to break the rules, just to prove that your contract aggressively rejects them. And as you're building this, keep this mindset front and center. Validation is a reusable public contract. Your authority checks and input validation aren't just one-off lines of code you throw in and forget about. They are reusable guards. By writing them cleanly now, the rest of your capstone project can call them consistently. Any input whatsoever that influences an account pointer or an array length absolutely must pass through this armored gate. Finally, we reach Section 5, the final inspection, pushing to green. Alright, the engine is built, it's tuned, and it's heavily armored. Now we initiate the rigorous checkpoint to determine if your module is truly ready for the big leagues. You really need to ask yourself, did your benchmark actually improve? And what does the word done genuinely look like in the context of advanced Web3 engineering? Because I'll tell you right now, done isn't just it compiles. No, done means it is battle-tested, highly performant, and securely locked down. So let's look at the specific acceptance criteria to get you there. Before you even think about attaching this module to your final project, you need a trifold verification check. Slice 1, functional tests pass, meaning your baseline logic works perfectly. Slice 2, performance metric met. You actively proved that 15% compute unit drop we talked about. And Slice 3, which honestly gets forgotten way too often, security rejections verified. Notice that it specifically says rejections verified. Your tests must definitively prove that bad actors are actively denied. All 3 of these slices must be green. Now, as enthusiastic as I am about perfect code, I also know for a fact that perfection is the enemy of progress. If you hit a wall, it's okay. Just remember to document your remaining trade-offs. Keep a really clear developer log detailing any follow-up refactors. This ensures that when you move to integrate this module later on, you aren't suddenly blindsided by technical debt. You'll have a clear map of exactly what needs smoothing out, rather than just a bunch of to-do, fix later comments that, let's be real, you'll inevitably ignore. So, I want to leave you with this final provocative thought. Is your module self-contained, thoroughly measured, and armored enough to face the final capstone dragon? I genuinely hope this explainer has given you the structured roadmap to answer that question with a resounding yes. As you continue your journey through these advanced Web3 concepts, remember that building robust smart contracts is an incredibly rewarding process. If you want to dive deeper into these programs and explore a vast library of interactive courses, I highly encourage you to visit forge.college. It's a fantastic educational resource to master all things Web3. Keep building, keep measuring, and I'll catch you in the next explainer.